Okay, let's do some more coding with lists. This is really fun. This recursive stuff. I have to prove to you that recursive definition of functions is so much easier than using all these loops. Right? So let's define a function that sums up a list of, let's say, integers. I could do num as well, but let's say integers. So sum is a function that takes a list of ints and returns a single int, which just accumulates all the integers, sums them, right? So by now you all know how to do this, right? Two patterns, empty and x's, right? Standard stuff. Equals. Now what should we put as a sum of an empty list? Any ideas? 0, huh? 0. Makes sense.
Default bit.
Yeah. Now this, if a sum has, if you apply sum to a head and a tail, then you have to add the value of the head, right? Plus the sum of the tail. And the sum of the tail is just the sum of the tail, right? I use words and then I write it the same way as I say it. Isn't that beautiful?
Well, that's why English is the best language, because it's the only language where the words come in the same order that I think them.
Same order as what?
As I think them.
As he thinks them. Yeah.
Subject, verb, object.
Okay. So this is sum. Now let's do one more product. Right? I mean, this is getting boring, doesn't it? Okay. All right. Let's say double. Double for a change. You know.
Bring it.
And it returns a double. Okay. So, okay, it's really, really boring. Oh man, I'm just like falling asleep doing this. Okay, so a product of an empty list, what should it be? 1? Who's for 1? Who thinks the product of an empty list is 1? And who thinks the product of an empty list should be 0? Anybody? I mean, the odds for 0 are much higher. You know, you get much bigger payoff. Infinitely bigger payoff, in fact. Okay. Yes, it's 1. Why is it 1? It's very important because when you do this recursion, right? The second thing that comes is the recursion. The recursion works this way. You know, you recurse into shorter and shorter and shorter lists because you can't calculate the tail, and in order to calculate the sum of the tail, you calculate the sum of its tail, tail of the tail of the tail, and so on, and eventually you get the product of an empty list. And if the product of an empty list were 0, then it would just cancel the whole result, right? So x is, you know, equals x times product of x's, right? And if x is empty, then this will return 1, so it will be x times 1, and that's what we want.
All right, so question. Could we express in the pattern matching notation 0, if the head is 0 and the tail is any list, then the product is 0. And that way we don't ever have to evaluate the product.
Much better.
Yeah. What is it called? The patterns.
Well, you can't
After
pattern
the
match
bar,
values.
what is it called?
You only pattern match on types. So you
Otherwise.
guard expressions.
Otherwise?
Option guard.
Guard. Thank you. It's a guard.
Yes.
So you can put a guard there. And
That's. I mean, it's equivalent to saying, you know, case x of 0. These should is to like a case or an if then.
yeah. But let's not go into it because
Let's not go into it.
all right. People want me to go faster and stall.
The important thing is you can't pattern match on
Okay,
the
so
value.
have you noticed how bored I was and sleepy doing this? This is almost the same code for sum and product, right? We should abstract it. So how do we abstract things? Well, we look at the differences, right? What's the difference between this and this? Okay, so let me just like underscore the differences here. I'm gonna use this. Okay, there's definitely a difference in here. Right? Here I started with 0, here I'm starting with 1. Right? Oh, and let me write this plus in the not the infix notation, but as a function, right? Because this is all functions. So it's a function of plus of x and some x's. Now I have two parentheses, right? Because I have a space here. And same here. We'll use the product not in an infix notation, but like this. Okay? So these are the differences. The difference is in the initial value, or maybe the terminal value of our accumulator. May I call it an accumulator, right? It starts with 0, and here it starts with 1. And there's a different function for accumulating. It's a binary function. It takes 2 arguments. Sometimes it's an infix, but not always. You can use any function here, right? So it's a function of 2 arguments. One of them is definitely of the type of the list element, right? This is the list element. This is the head, right? And here also it's the head of the list. Okay? The second one, though, doesn't have to be. Okay? The accumulator could be any. So, by the magic of Haskell, it's very easy to abstract this. So we'll define a new function, and we'll call this function fold, because it's folding the list, right? But it's folding the list from the right. There is actually a difference in folding from the right and from the left. Not when you have operator plus or times, because it doesn't matter, unless you were using doubles and you overflow, right? Or precision problems. But so let's define fold R. So what arguments should it take? Okay, it will be folding a list of A's, right? So the first argument will be this function, right? Let's take this. So it's either a plus function or a times function. So it's a function, but it's a binary function. So it's a function of 2 arguments. One argument, another argument, and it returns something. So it will be like a function with 3 types in. And we'll write these types in separately. Okay? Now the other thing that's varying is this accumulator. Okay, let's call the type of accumulator B. Okay? So it takes these 2 things, and then, just like the sum and product takes a list. So it takes a list of A's, and it returns the final accumulator of type B. right? So it starts with this accumulator at 0 or at 1 or at something else, right? And just keeps accumulating and finally returns this accumulator, like the sum of the whole list. Okay, so let's go back to this. So this function, look how we are applying this function. We are applying it definitely if the first argument is the head of the list, so it's of type A, right? Must be of type A. The second is actually the type of the result of product or the result of sum, right? Which is the same as the type of the accumulator. Now in our case, these were the same types, but so this is like the previous value of the accumulator, and it returns the new value of the accumulator. Right? So that's the signature of Foldable. Now the implementation of Foldable. So we provide this function, what do I call it, f? Yeah, I'll call it f. It's a 2-argument function, right? So we provide the function, we provide the initial value of the accumulator, let's call it z for 0, and we provide a list, and now we have to do pattern matching on the list, right? On the third argument. So the first pattern is an empty list, and the second pattern is a cons of x axis, right? So we do this pattern matching on the third argument, right? These are the parameters for Foldable that make it either of sum or product or something. Okay. Now we have to define these things. Okay, so what's this stuff acting on an empty list? Right, on an empty list, here it was 0, here it was 1. That's the varying thing, right? That's the initial value of the accumulator. The initial value of the accumulator is z. Right? Here it's 0, here it's 1, and yeah. Now for this guy, what we are doing, we are applying this function of 2 arguments. Here it's a plus, here it's a star. We're applying this function that we call f now to 2 arguments. One argument is the head of the list, so it's an x. The second argument is our function acting on xs. So this is where the recursion comes in. So it will be our Foldable acting with fz acting on xs. Okay, and that's it, right? It's a recursive function, just like these two. And now, if you replace, z with 0 and f with plus, you get sum. If you replace z with 1 and f is with times, you get product. And you can get many more other things. And in fact, there is a whole class of data types. Not only lists that can be folded. And these data types that can be folded are called foldable, obviously, right? Okay. So that's cool that you can do abstraction. It's such an easy way in Haskell, right? Try doing this kind of abstraction in C++. I don't even think they have a function fold. They have something. Yeah, what is it called? Accumulate. Okay, so that's accumulate. But it's a template. It's like if you look at the implementation of it, it's mind-blowing.
Well, parametric polymorphism is very much like template instantiation.
What did you say?
Parametric polymorphism in Haskell is very much like template instantiation in C++.
Yes, right.
No angle brackets.
Yeah, the angle brackets.
Isomorphic.
Right. But you use a different syntax
Oh, yeah,
for
syntax
this,
is-
right?
And
Here you use the same syntax. So I told you about this thing that in Haskell we can actually do mathematical proofs of properties of our code. In case of lists, we can also do proofs. But since lists are recursive data structures, and functions are recursive, we'll have to do some kind of recursive proofs, right? You know what recursive proofs are called in mathematics? Induction, right, exactly. So if you want to prove something about a function that's written recursively, you will have to use induction. Okay? You remember how induction works? That you have the base case, and then you say if this is true for n, then and I can prove that from the fact that it's true for n, I can derive that it's true for n plus 1, then it must be true for every number, right? Now here it's a little bit different, okay? But that's slightly different. Let's show the following theorem, okay? Oh, this is a very complex theorem. The length of any list is greater or equal than 0. Is that true?
Yes.
How do you know?
Induction.
Okay. You're ahead of me. Okay. Well, let's first define what length is, right? Oh, I mean, we have already done this, right? But its definition is recursive, right? So the length of x colon x's is equal 1 plus length of x's, right? And actually, I don't. Well, I'll keep the x. It's a wild card, right? Okay. So obviously, this shows that length of an empty list is 0, which is definitely greater or equal than 0. Fine. But this guy, it's not so clear, right? 1 plus something. It's 1 plus something. Well, as long as this something is greater or equal than 0, then this is definitely greater or equal than 0. But this actually is what we are trying to prove, right? What if this is minus 2? Well, the length of this list would be 1 minus 2 would be negative. Huh? I can't come up with any example of a list whose length would be minus 2, negative 2, right? But this is not a good kind of reasoning, like in concurrent programming especially. I can't come up with any scenario in which this would deadlock. Let's ship it, right? So, but in the Haskell you can actually do it correctly, because you can say, okay, so this is my base case in induction, right? The base case is that for an empty list, this theorem is true, right? This is my theorem. Now let's assume that this is true for all lists that are kind of smaller of what I'm now trying to prove. So if this is true, this theorem is true for len xs, then 1 plus something that's greater than or equal to 0 is also greater than equal to 0. So I have proven this by assuming this. So this is my induction step. I assume this, and I prove this, and therefore it's true for all lists. Okay? Now, you might say, okay, you are cheating, right? Am I cheating? How am I cheating here? So I said induction is for numbers, right?
Right. How do we know that the inductive property holds on lists?
Right. I'm doing induction on lists, and this is called structural induction. Okay, we have mathematicians here. Thank you. So structural induction can be used in any case where we have some kind of ordering, right? We need some kind of ordering to say that this list is lesser than this list on the left, right? It's let's say a sublist of this one, okay? So we have this relation called being a sublist of something. This is not a total order, you know. There could be two lists that are not a sublist of each other, right? So it's partial order. So induction works only, structural induction works only on things that have partial order. But that's not enough, because like you can do this induction, you know, and never reach the base case. It just can go on and on and on and on, right? There's no base case. So the existence of the base case in structural induction means it's called by mathematicians, it's called that the set is well-founded. Well-founded, it means that every sequence of sub lists eventually ends in something that has a bottom, right? It has a bottom. And the bottom of list when you do sub is an empty list. So that's why it works. So hooray, mathematics. Okay, now let's do another recursive data structure to show you that actually there is more than a list in this world. So let's define a recursive data structure that is called a tree. Tree that contains elements of type A. Okay, tree of A. Okay, tree of A. So I'll say data, right? Tree of A equals. And just like with a list, I have to have something that's an empty list, right? An empty list. So I don't know, what should I call it? How about empty? Okay, so this is how we construct an empty list. How do we construct a non-empty list? Well, a non-empty list is a node. So we'll call this constructor a node. And what does a node have in it? It has the left branch, the value, and the right branch. So this is the kind of tree that stores values in the nodes. Right? And the sentinels at the end, the leaves are empty lists. So it's a node, and it has a tree of A, and A, the value that we keep here, and a tree of A. So this is the left branch, this is the right branch. Right? So it's a binary tree. So here's a node that has left branch, right branch, and some value 1, 2, 3. Right? And this will have left and right branch, and these could be empty. Right? Let's just call them empty. Empty lists are just leaves. Now this is a perfectly balanced tree, but in general they are. So, how do we define a function? Let's define a function sum. Let's call it sum tree. Sum t, let's say. Okay? Sum t that takes a tree. That takes a tree, well, let's say of int, okay? But in general, it should be num, because we are summing them, so it has to be tree of int and produces an int, okay? Just sums up all the nodes. So just like before, you know, some t of an empty tree, right? The first constructor, well, obviously 0. Some t of a node. So remember, patterns have to be in parentheses if they contain more than one thing. This pattern, empty, it's just one thing, so you don't need to be parentheses. But if there's a node of, so there will be a node that has a left subtree, some value x, and the right subtree. Okay. This is a tree. This is a tree. This is a value of type A. I'm matching this and like extracting 2 trees and 1 value from this node. Right? And this is also boring, right? I mean, so yeah, some t of L plus x plus some t of right. So again, it's recursive, right? I have to calculate the sum of the left subtree, sum of the right subtree, and the value in the node. Right? So it's very simple, right? In general, I would say, okay, this tree is foldable, right? Because I can fold it, and I could write the fold function for it. And actually, foldable can be the easier way of understanding foldable is that it can be always converted to a list. Can we convert a tree to a list? That's what we are doing, right? We are doing the in order.
Where do you get that foldable is equivalent to being convertible to a list?
Because it has a toList function method. All foldables have a toList method. They have to have.
You're cheating.
Yeah. Which means that you can traverse it. It just means that there is a way to traverse it. Like here, the in order traverse, right?
There's also
Traversable and foldable are completely different notions, aren't they?
Okay, traversable is the same as foldable, plus it's a functor. And I haven't talked about functors yet, but I would love to. If you don't interrupt me,
Bring the fun back, man.
And in fact, you know, since you asked, we can define a map on a tree, just like we define map on a list. Okay, map tree would be something that takes a function from A to B, right? But it takes a tree of A, applies the function to every node, and produces a tree of B. Right? So we can actually do mapping of trees as well. That's why it's traversable. Okay? So this is again a boring thing, but it's a good exercise. So map T, F, empty equals empty, right? Applying a function to an empty tree does return an empty tree. But map T, some function, and a node is better, right? Because what do we have? We have to apply the function to this x, and we have to apply map T to L, map T to R, right? And reconstruct the node from these 3 things. So we'll reconstruct a node by the first element is applying map T to L, then applying F to X, and finally applying map T to right. Right? I mean, if you look at it, there's nothing else you can do. This is a really obvious thing to do, right? You apply the function to the value in the node, and you recursively go into left and right subtrees and apply the function to the subtrees. And applying function to subtrees means calling recursively the function that we are just defining. So first let me explain what the intuition is behind a functor. So the simplest intuition is, if we don't want to get into category theory, is that a functor is sort of like a container. It's a container of A's. Okay, so a container has a shape and it has the contents. So if we have a container of A, it means that the contents of this is of type A, but we have to define a shape for it. So the fact that the container is parameterized by the type of its contents means that it has to be polymorphic in its contents, right? So the container, first of all, has to define this shape, and this shape is really independent of what it's holding, whether it's holding apples or oranges, doesn't matter. You know, it's a container that can fit anything. That's not really like in real life, right? It's a container in which each node, each cell is expandable, so you can put like a aircraft carrier in it, or a grain of sand. So this fact means that a functor must be a type constructor. And it means that if it's parameterized by some type of the contents, right, that it has to be a type constructor. It's just a way of constructing a type from any type of contents. So that's the first part of a functor, type constructor. That has to be polymorphic. And the second part of a functor is that there must be a way, you have to define a way of modifying uniformly the contents of the container, which is exactly what our map did and map T did, okay? It applies a function to every element stored in the container, and the important thing is it doesn't change the shape of the container, right? When acting on a node, it returns a node of the same shape. When acting on an empty, it returns an empty. So it never changes the shape of the container. It just recreates the same container, but with modified contents. And something like this is called a functor. And let me give you yet another example of a functor. So we know that map and map T are functors, but maybe is also a functor, right? Maybe is a type constructor. Maybe A, and it's either nothing or just A. So it is a type constructor, it takes an arbitrary A, and it's sort of like a container that can contain nothing whatsoever, or it can contain one element. Right? These guys could contain as many as we want to put in them. This is a container that can contain only one element at the most, right? Either 0 or 1, right? And for it, we can also define a map. Let's say, well, I don't know, I call it M. Let's call it map, okay? So map of nothing is nothing. Yeah. Map of just X. I forgot the F. I'm applying a function F to it. Right? So it has to cannot change the shape, so it still has to be just. It has to be this one element thing, but it changes the content by applying the function f to it. Right? So that's sort of obvious. This is one of these map things. Only I'll call it map m. Even though map m is used for monads rather than maybes. So now we have these 3 examples, and I'm getting really, really bored writing this stuff, okay? So I want to abstract. I don't like boring jobs, menial jobs, okay? That's why I want to program in Haskell, because every time I find something boring, I go and I abstract it, okay? Well, not, I mean, this is abstracted in the standard library already for me, right? But I want to show you that how easy it is to do this abstraction. But this is a bit tricky, okay? Because the difference between all of these guys is that they use a different type constructor. Okay? They differ by type constructor. One uses the tree type constructor, the other is using the list type constructor, and this is using the maybe type constructor. So I have to do something that's abstract, not in some value or type. It's abstract in a type constructor. So I need to write some kind of template to which argument is the type constructor. Okay? So like in C++, you know, you would say, I know, there's something called template parameter, right? That's sort of like a type constructor, okay? But in Haskell, you know, once you know how to abstract things, who cares whether it's a type or a value or a type constructor? Just give it a name, lowercase name, and say, well, this is not really a type, it's a type constructor. So deal with it. Okay? So now a functor is really a whole class of types, right? I'm trying to define a whole class of types that have this property that they are constructed using a one argument type constructor, and then they have this function that maps a function over it, right? So this is a whole big class to which I know some members of this class. One is tree, one is list, one is maybe, okay? So maybe I can erase some of this stuff and just remember this stuff, okay? Memorize it quickly. And I want to define this class of types. Okay, so what do I call this? What should I call this? How about if I call it a class? So I'm defining a class. Now the class of these types will be called functors. I'm defining a functor. Okay, I'm using capital letter. This is when I define type or class of types. It has something to do with types. So class functor. And now I have to give some kind of name to it. I'll use the letter F, okay, for this functor. I mean, it's kind of confusing because we use F for functions as well. But in a sense, this is a function on types, so it's a function. Now, I should mention that this F is a type constructor here. Okay, it's not a type, it's a type constructor. So its kind, if I can use kinds, is star, arrow, star. So it's something that takes a type and produces a type. So it's like a maybe of A produces maybe takes an A and produces maybe of A, right? So this is the kind, this guy F. And I could, in principle, say, you know, F colon colon star arrow star. I don't need it. It's possible to say that, but the compiler doesn't really need that. I'll show you why it doesn't need that. It will figure it out, right? So the syntax for defining a class is class name, then the variable that denotes the type of this class or type constructor, and where. And after where follows the definition of like what are the properties of this class. And this particular class must have a method, you could say, but must define a function called fmap. So fmap is the generalization of all these maps, map tree, map list, map maybe. This is a function, a method of the functor, you can say, that has the following signature, right? So it takes a function from A to B, right? All of them were taking a function from A to B to apply it to what? To FA. Okay? So list of A, tree of A, maybe of A. Right? And what does it produce? It produces another F of A. Right?
FB.
Sorry, BB. Yes, thank you. Yeah, absolutely. And that's it. See, every functor that I defined, I didn't tell you that these were functors, but every one of them had a function of this type under different names, right? But it was always, takes a function and transforms a container of A into a container of B's. Okay? So, that really saves me a lot of thinking, right? If I know that there is an abstract class called functor that abstracts all these guys. Now, how? Oh, okay, I told you that the compiler figures out that F is a type constructor. Why? Because it's applied to a type. Right? If A and B are types, this is just a regular function, then F must be a type constructor because it's applied to a type. If it were applied to a value, then it would be function, right? But it's applied to a type, so it has to be a type function. So the compiler will look at this and say, F, it must be a type constructor, right?
And if you wanted to write the type
Kind signature.
explicitly, you could not, or you could.
No, I could. I wrote before the type kind signature for F. The compiler would accept it, and of course you would say, you know, you have to put this pragma kind signatures or something like that, right? And now but the compiler will not figure out by itself that maybe or list. Well, it knows about list, but let's suppose it doesn't know, right? So by itself, it cannot figure out that these are functors, right? I mean, they all have some functions that have the same signature, but are these the functions that correspond to fmap or not? We don't know, right? So we have to tell the compiler. And for all these classes that I showed you, except for tree, you know, it's already defined in Prelude that they are functors. But for a tree, you would have to say it yourself. So to say that something, some type constructor actually is a functor, you say that it's an instance of a class. So these are called type classes, and these are called instances of type classes. Instance, you give it the name of the class, functor, and we want to say that tree is a functor. And notice, I said tree. I didn't say tree of A. Why? Because I'm supposed to provide a type constructor that requires a type as an argument to produce a type. Tree itself is a type constructor. Okay? So I'm showing that tree is a functor. And to show this, I have to say what fmap is. I have to define fmap. Right? Now I have an easy thing to do, because I can just say fmap is equal map t. And that's it, right? I mean, normally when people define one function in terms of another, they have to specify the arguments and just repeat them on the right-hand side, right? But in Haskell, you can say one function is equal another function. It's just equal, okay? Obviously, for any arguments. But you don't have to specify the argument. This is like a point-free notation for the quality of the functions. And you can do, you can put a regular definition of a function here, It doesn't have to be just equal to some other function. You can define your function, right? Implement your function right here. You can implement fmap right here. So I could have put, fmap of some f empty equals empty, and fmap of node blah 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 equals node blah blah blah. Right? I could have done this right here on the spot. I just wanted to show you first the implementation, but you can just implement it right here on the spot inside the instance definition. Right? Now I want you to understand that these functors that there is a functor that's really trivial. It's called the identity functor. It just encapsulates whatever type you give it. It sort of encapsulates this type. So it just contains this type, nothing else, right? So there is a functor called identity, and how do we define identity on types? So we say data. Let's call it I. For simplicity, it's a type constructor that takes an A, and there's one constructor which we will call I as well, that takes an A. So it looks like the function ID, right? Exactly. But this is an ID on types. So this is it's called an identity functor, and obviously it's an instance of functor. So what do I put here?
Where?
After functor. I, right? Type constructor. This guy. Not this guy. This isn't normal. This guy. And I define fmap. I pattern match on this constructor. So that's this guy again. Let's call it x, right? Fmap f, right? And what do I do? Well, I just don't change the shape, please, right? Just reconstruct the shape, but apply f to x. So this is really application of function application to x, but in a fancy way. that you know, hidden in a box. This A is hidden in the box instead of being like in the open. But it's really function application to this value, right? So it's pretty trivial. I want you to remember this identity functor, because this identity functor is also a monad, and sometimes people say that, you know, a monad is about side effects. Well, what kind of side effects is an identity, right? No side effect. So monad is not really about side effects. Now you learn something that will like ruin your reading of all other book about Haskell. Okay. Now I want to show you an unusual container. Something that people say, aha, this is a counterexample, because it's a functor, but it's not really a container. And I say, okay, because you are narrow-minded about defining containers, you know? Like you've seen only these few containers and you think you know what a container is. No, a container could be a function, right? Think of a function as returning some values, but I think of a function as just a container that contains these values. And if you want to retrieve a value from this container, you have to provide a key or an index into it. That's the argument to the function. Give me an index into my storage, right? And I'll give you the value from my container, right? That's a container. I mean, especially if it's like a container of bool, you know, okay, I'm storing only two values, right? Okay. So, how do we define this fact that the function is a container? So we have to define a data type. Now this data type, well, the name for this type constructor is reader. And you will see why it's a reader when we talk about monads, because these functions that I've shown you actually are all monads. Reader takes two types as arguments, right? Let's call them E and A. Now I call it E because when you see that as a monad, this will actually correspond to some kind of environment, the monad that has access to some environment. So this is environment, and this is the free variable A, type variable A, that we will use to define a functor. We'll just keep this constant and vary A. Okay? So let's say it has a constructor, data constructor that we will also call reader, because I want to inoculate you to this style that you're not always shocked. Oh, this is data constructor or type constructor. They can have the same name. So reader takes, when you construct a reader, you give it a function from E to A. Okay, so the constructor takes a function from E to A. So reader really encapsulates this function. Reader is this function. That's the truth. Reader is this function, but encapsulated, because if we don't encapsulate it in some data structure, then the compiler will complain that, oh, you cannot use type synonyms with classes, blah blah blah. Okay, so we'll indulge. Okay, so is this an instance of functor?
Sorry, pardon us?
Yeah? Did I do something crazy?
Yeah, you defined a reader, and the constructor has as parameter not an E and an A, but a map from E to A.
Well, remember, this is type constructor. It takes types.
Two types.
This is data constructor. I'm defining a data constructor. I can give it whatever I want. I'm just saying, in order to construct a reader parameterized by E and A, you have to give a function from E to A. That's how I define reader. Okay. Give me a function. And then when I pattern match a reader, I will extract this function. I just want to show that a function thinly encapsulated by reader, that this function actually, function type is a functor. Okay? So, instance of functor, it has to take a type constructor of a single argument, right? But this guy takes 2 arguments. But partial application. Reader of E is a type constructor. It requires another thing. It requires an A. So it's partially applied type constructor that takes 2 arguments. It's applied to 1 argument. It requires still an A. Okay? And now we have to define F. So since we have functions and functors that use the same letters, let's say f map of g. Okay, so this is the function, and I'll write here, this is function from A to B. Right? The first argument to f map is a function from A to B. Okay? And it takes a reader of, it takes as the first argument, right? Reader, and it should be reader of EA, right? So here this reader will contain a function f whose type is E to A. So the type of this whole thing is reader EA, and this is a data constructor. Data constructor contains a function f that goes from E to A. Yeah? It's like kind of several levels that you have to go through. But this is reader of EA, and it contains inside a function f that's from E to A. Right? And what should it return? Okay, it should return some kind of reader. It should return a reader whose type is reader of EB, right? Because this function transforms from E to B, right? So it has to be a reader from E to B, which means it's a reader of some function, you know, f prime, whose type signature is E to B. Okay? So how do we get a function like this that goes from E to B? We have at our disposal 2 functions, A to B and E to A. Can we just manipulate them a little bit to get a function from E to B? Okay, well, from E to A and then from A to B, right? That's a function composition. So if we compose G after F, G after F, then exactly we get from E to B, right? Function composition. So F mapping is really equivalent to pre-applying a function, prepending a function. The final thing, and I don't know, maybe this is what Alan was talking about. The final thing is that something that we cannot really express in Haskell, but we kind of know that it has to be true. If something is a real functor, it has to follow certain, it has to have certain properties that are not expressible in Haskell. These properties are kind of trivial, you know, like one property, it's called sometimes axioms, right? One axiom of a functor is that, I Identity, right? Fmap, if you put an identity function here, you apply the identity function to all elements of a container, what should you get? You should get the same container, right? Which in this notation, 0.3 notation, I can write it like this. And look, this is identity that has a signature from A to A. This is an identity, the signature is actually FA to FA. Right? So ID is something else on the left side and on the right side. And this is also very characteristic. And the second law is called the fusion law. It says that if you apply fmap twice, so if you apply fmap G after applying fmap F to some container, right? So you actually, like, you know, so you go through this container and apply F to each element. Then you go through this container again and you apply G to each element, okay? Why not simplify this work and say, I'm gonna go once to the container, but I will apply G after F. Once, okay? The result is the same, okay? Now, the interesting thing is that this first one, you actually have to check, okay? Whether your thing is really a functor, you have to check this property. This property actually follows. This property in Haskell is a free theorem. Okay? It can be proven. Not in category theory though. In general, it's not true. Okay, that's it for today.
All right.
Thank you. I did functors.